A very good morning. Today we are going to see about the unit commitment problem. Already we have seen the economic load dispatch problem and we have solved many problems. In this class, we are going to see about the unit commitment problem. So generally, what is meant by unit commitment problem in the sense? Unit commitment problem is defined as committing the generating units with sufficient generation capacity. Committing the generation unit with sufficient power generating capacity to meet out the demand optimally. Okay. So whereas in economic load dispatch, we are minimizing the total fuel cost by optimal allocation of generating units. Whereas here after first you have to do with the unit commitment problem, then only you have to go for your economic load dispatch problem, because we have to commit which unit we have to select. So that's why committing the generating units with the sufficient generation capacity to meet out the demand optimally. So that is called your unit commitment problem. So, and also to obtain the reliable and economic supply for the given load. To obtain the reliable and economic supply. Reliable means 24 by 7. 24 by 7, you have to provide, we have to provide the, that is power generating companies have to provide the supply to the consumers, and also economical supply. So we have to supply the economical thing to the load. Why? Because if you are uneconomical, then similarly you are operating the generating units. Similarly, you are operating the generating units. So in that scenario, your tariff will goes high. So we have to obtain the reliable and economical supply for the given load. So there are many constraints in the unit commitment problem. Thermal constraints is there, then hydro constraints is there, hydro unit constraints is there, thermal unit constraints and hydro unit constraints. So why we are considering only these two constraints in the sense? So these two generating units only constitutes the maximum generation, like maximum generation. If you take like thermal is the first thing, then secondly we are more reliable on the hydro. Then only your renewable and all coming into the account. So now nowadays they are concerned about the renewable. Why? Because hydro also will give hand sometimes, and it will not give some other times. So nowadays they are going little bit. They are moving on to renewable energy resources, but we can't predict from renewable energy resources we can generate this much, only based on the weather report, and that too even though we are forecasting, sometimes the weather may be changing. So the forecasted weather report will not be same always. They will tell like today it will rain, sometimes it will not rain. They will tell like today the wind velocity is of 40 kilometers per hour. Sometimes that might not be possible. Few times, many a times it is possible, but sometimes. So that's why we are relying on this thermal generating unit, and as well as hydro generating unit at the majority of the time. So coming to the thermal units, so thermal units usually requires a crew. Crew means more number of people, more number of people to operate, especially when turned on and turned off. Like if you take like a roll call of thermal generating units, so minimum 300 people may be working in a particular plant. if you take in a one shift, one 300 people will goes from 300 to 500 people may go in, and to operate that particular plant. Why? Because that many operation is there, that many operations we need to do. And also for working, it is not a very simple task like you can simply go and you can on like that. Like from starting from the coal handling plant, ash handling plant, up to the last water treatment plant, and like cooling tower, then um, like fume outlet, everything. It is very very concerned under boiler, furnace, then superheater, preheater, air preheater, then economizer, turbine, then generator, like that. Many things are there. In that, you need to monitor the pressure correctly. If the pressure is very low, then sometimes your efficiency of the generator will goes down, like that. In each and every place is starting from the boiler temperature, they have to maintain. So in that particular place, some 10 to 20 people may work in and around the boiler. Then coming to the furnace also. Then similarly, like steam outlet tube. So pressure monitoring. After that, like low pressure turbine is there, high pressure turbine is there. Like that turbine you need to take care of. Then generator you need to take care of. Then like water treatment plant. After that, that water treatment plant, for the waste steam get condensed, and again it should be converted to the somewhat pure water. A normal pH of water you need to convert. Again, it may be fed into the boiler, and the boiler maintenance, like that. Many processes there. So definitely crew might be of very very more, like 300 peoples may be working in a one crew. Like in a one shift. So a thermal unit undergo only gradual temperature changes, and this translates into a time period of some hours required to bring the unit online. So definitely, if you want to generate power at so say 9 o'clock, 9 a.m. in the morning, 9 a.m. in the morning. So this crew has to work so like 2 hours before itself. From 7 o'clock, they have to start the process. Then only from 9 o'clock you can generate, say in the particular generating unit, if they are going to generate, if they are planning to generate 1500 megawatt today. So 1500 for generating the 1500 megawatt plant. So there will be 500 into 3 or 1000 into 1 in plus 500 into 1 megawatt generator will be there. So what they will do is first they will start the 1000 megawatt. Slowly they will start. So after that, the same crew goes for second unit, and they will operate. Why? Because some few crews after starting up, after that they may go to second plant, and they may operate. Why? Because if they operate simultaneously, this like 300 members may be working in a one for one generating to maintain one generating unit. So again, for operating another generating unit, it might take like another 50 to 100 employees to operate. So like another 100 people who will give the salaries, wages to the employees. So what they will do is they will go for first generating unit, starting the first generating unit. After sometimes, when this is in operation, then few workers may be there, few employees may be there to monitor all the pressure, then temperature, like that. And some other workers may shift to second unit. They may operate the second generating unit. As a result, such a restriction in the operation of thermal power plant, various constraints arise, such as minimum uptime constraints, minimum downtime time constraints. What is minimum uptime constraints? Once the unit, once the thermal unit is running, it should not be turned off immediately. Why? Because that is not a very simple process. Like as like in your home loads, you can't simply go and off the switches so that all the loads will be off. If the unit is operating, okay, there should be some minimum time is there, minimum time, so that you can off the that thermal power plant. Say for example, from 9 o'clock to 2 p.m. they may plan to operate. They may plan to operate 9 o'clock to 2 p.m. So, like 2 p.m., if they want to off now, from 1 o'clock itself, they may reduce the like boiler temperature, then the furnace temperature, like that slowly, like 1:30 onwards, they will slowly off. So it will take 1 hour time, 1 hour time to off itself, to make it off itself. Why? Because in the boiler, water might be simply boiling, so that heat we have to extract the maximum. Why? Because we are spending very more and more of amount, like coal. We are spending more amount for purchasing the coal, so we have to extract maximum power out of that. So slowly, the heat to the furnace we have to reduce. Then the boiler temperature, then steam we have to reduce. Slowly like that only we have to stop. So it will take some time to emergency stop you can do. Emergency stop you can do, but not in the boiler or a furnace like that. So sometimes if you see in your news channels, like some thermal unit got fired in boiler furnace. In today, 1,000 megawatt will not coming to our state, or 1,500 megawatt, 2,000 megawatt will not come to our state. Like that, some many accidents also happening once in a while, yearly once or twice, some small accidents are happening. So it will take some more time. Once the unit is operating, it should not be turned off immediately. That is called minimum uptime constraint. So next is minimum downtime constraints. Once the unit is decommitted, that is the minimum time before it can be recommitted. Actually, decommitted means once the unit is off, then there is a minimum time before it should be started. That is recommitted. Before it should be recommitted. So there should be if the once the unit is decommitted, that is off. That is some minimum time, because everything has to be settled down. Every process, the like steam pressure in that particular steam valve, steam tubes, then boiler temperature, furnace temperature has to be settled down for some time. Few time is required. Some time is required to stop, like simply like that. If we are stopping, after that, some time is required to recommit also. Recommit means to start also, as I said, like 2 hours minimum. It should be required to start the whole plant. So those who are entering into shift, 6 o'clock early morning shift, so they may start their work from slowly from 7 o'clock, so that they may go for operation, like generation, to the particular grid from 9 o'clock. So that's why, so minimum time before it should be decommit, that is called minimum downtime constraints. So minimum uptime constraint is, once the unit is running, you should not turn off immediately. Like hydropower plant, it is very easy to turn off also, or very easy to it will take some 10 minutes, 15 minutes, more than that, more than half an hour it will take. So not thermal power plant 2 hours like that. only 10 to 15 minutes you can easily start the process. Once you get the clearance from your like a PWD, Public Works Department, like we are going to start like a 100 megawatt generator or 500 megawatt generator or 200 megawatt generator. So simply like that, once amount of water is being confirmed, then you can simply go for the operation. But whereas in thermal units, it will take many time, like take more time, so that the plant to be in operation. So that is called your minimum uptime and minimum downtime constraint. So you have to write with an example. Simply like that, don't write this definition alone. You have to write with the example, so that it is easy to understand. Next is crew constraints. If the plant consists of two or more units, they cannot both turned on at the same time, since there are not enough crew members to attend both units while starting up. So there are two or more units. One unit, three unit generator, three generating units are there. Three generators are there. If they will not turn on all the three units at a time. Why? Because there is no enough crew. Why? Because only 200 employees, 300 employees only entering into the particular shift to operate that particular thermal generating units. So if you want to on another plant means, you need some more workers, some more 100 workers more to operate the second generating units. Again, third generating units, again 50 workers. So they will not start at the same time. So one unit they will start after it comes into the operation. After 2 hours, it comes to the operation. Slowly they will move on to the second operation of second generating unit. But there are some employees to monitor the first generating unit also. The pressure, steam temperature, then everything they will be monitored. So that is called the crew constraint. So enough crews members to attend both the units while starting up. In addition, because the temperature must be moved slowly, a certain amount of energy must be expended to bring the unit online. So temperature and pressure of the thermal unit, what they will do is they will be starting slowly only. So simply like that, we can't bring the temperature to 600 degrees Celsius, 700, 800 degrees Celsius. Simply like that, we can't make. Why? Because for boiling, even in our home, for boiling 100 degrees Celsius, like water we are boiling, no? For boiling 100 degrees Celsius, minimum it is taking. It depends on the amount of water. Minimum, if you take 1 liter, minimum it takes 10 to 15 minutes, 1 liter itself. For boiling 1 liter itself, 10 to 15 minutes it is taking to reach 100 degrees Celsius. So imagine 600 degrees Celsius, 600 degrees Celsius. So boiler is of very big, 10 feet, 15 feet boiler. So volume of the boiler also will be of very more. So that much amount of water also will be there. So the that whole water has to be get heated up within some like 2 hours, 3 hours it will take. So the whole water has to be heated up, uh, not to 100 degree, to 600 degree, 550 degree, 500 degree Celsius. So furnace they will heat up to 600 degrees Celsius. Water, like some losses will be there now from furnace to the boiler. So water might be of some losses, some 50 degrees Celsius might be of some losses might be there. So that losses, 550 degrees Celsius or 500 degrees Celsius, that water has to be heated up. So from that water, superheated steam, not normal steam, like we are inhaling, no. So we are taking steam bath, steam inhalation. So in that scenario, what we are doing is we are heating the boiler. Sorry, we are heating the water up to like 100 degree or more than that, little bit more than that. Like if you measure the temperature, little bit more than that. So 150 degrees Celsius or 120 degrees Celsius, so that the steam will come more, so that you can inhale also. While inhaling, you'll get more steam. So like that, that steam is not what we are inhaling. It is like 5 to 10 times more than that what we are inhaling, no, like 100 degree. So if you take out from the gas stove or from the induction, whatever it may be, so some temperature might be getting down. Okay, in gas stove, it will have 100 degrees Celsius. While taking it out, some 5 degrees Celsius or 10 degrees Celsius, the temperature may be getting down. So even though we are getting some steam, but this is the superheated steam. So that is hitting the turbine to turn. So that much 100 megawatt turbine, 1000 megawatt turbine. 1000 megawatt turbine means the runner, the turbine might be of, like, I will show you a video. Like the turbine may be of like this. So first is high pressure turbine, then again the low pressure turbine. So first it will turn, there will be a series of turbine, not only one runner will be there, there will be a series of turbine will be there. So that series of turbine, it has to be uh, it has to be turned, so that you can generate 1000 megawatt of power. So imagine how much uh, pressure needed to rotate that 1000 megawatt runner turbine. So the pressure might be of very very more. And if you say like this, energy does not result in any megawatt generation from unit, and it is brought into unit commitment as startup cost. Okay, so that is called startup cost. Okay, that is, in addition, the temperature and pressure of the thermal generating unit must be moved slowly. A certain amount of energy must be expended to bring the unit online. This energy, that is, that amount of energy, does not result in any megawatt generation from the unit, and it brought into the unit commitment problem as startup cost. So that cost is called startup cost. Okay, so startup cost maybe can be vary from maximum cold start value to much smaller value if the unit was only turned off recently and still relative close to operating temperature. Okay, so startup cost can be vary from a maximum cold start. Cold start means like a normal operation, no, normal operation, that water will be somewhat cool. So that is called cold start. So value much smaller if the unit was only turned off recently and still relatively close to be operating temperature. There are two approaches to treating a thermal unit during its down period. The first allows the unit boiler to cool down and then heat back to the operating temperature in the time for scheduled turn down. Okay, so there are two operators for treating the thermal unit during its down period. Down period. The first allows unit boiler to cool down. So while if you want to off now, so what they will do is first they will allow the unit boiler to cool down, then heat back to its operating temperature in the time for scheduled turn on. Okay, so again after 4 hours or like that, again it want to start up. So again the some temperature might be there in the water, so that what they will do is they can easily heat back to this operating temperature in a time for a scheduled turn on. So once it is off, so after 3 hours 4 hours, so again there might be a sudden demand. So we want to turn on the generator. So again there will be some water heat, some temperature will be there in the water, that is called scheduled to turn on. That secondly, the second called banking, which requires sufficient energy to be input to the boiler to just maintain the operating temperature. The cost of two can be operated so that it possible best approach, that is cooling on banking, can be chosen. Okay, so this startup cost when cooling, that includes CC into 1 minus this is zeta zeta power T by X into F, capital F plus CF. So where CC is nothing but cold start cost. Okay, in million British thermal unit. Then F is the fuel cost. F is the fuel cost. Then CF is nothing but fixed cost. Fixed cost includes the crew expense and maintenance expense. Okay, so that is the CF. Next is alpha, that is T divided by alpha. Alpha is nothing but thermal time constant for that particular unit. Time that unit was cooled. Unit was cooled. So startup cost while banking there is while cooling, there is while cooling, there is while banking. So there is a difference between cooling and banking. Okay, so banking requires sufficient energy to be input to the boiler to just maintain the operating temperature. So cooling already we discussed. So startup cost while banking, that is nothing but this C T into T into F plus CF. So where CT is nothing but cost of maintaining unit at operating temperature. Cost of maintaining unit at the operating temperature. For certain number of hours, the cost of banking will be less than the cost of the cooling. Okay, so up to certain hours, up to like 1 hour or 2 hours, there will be some heat will be there. So like if you are heating the water for taking bath, if you are heating water, then you are keeping it in the stove, that is gas stove. After sometimes what you are doing is you are just turning off your stove, and what you are doing is you are keeping that vessel somewhat in some places. So after half an hour also that some temperature will be lost, like some heating will be lost. But even then, that heating will be remains for some hours, some 1 hour like that. That heat will remains. If you just close with a lid, that will be remains for few hours. 1 hour, minimum 1 hour. That heat might be there. So, so that is called banking. So that temperature, with that temperature, again we can easily start up the next that is next operation for after sometimes after some hours of time. So simply like that we can on. Finally, the capacity limits of thermal units may change frequently due to the maintenance or unscheduled outages of various equipment in the plant. This must be taken into account in the unit commitment. So next is the other constraints. So this is called cooling and banking. So time dependent startup cost. Time dependent startup cost. So this axis in hours. 1, 2, 3, 4, 5. Like this axis in hours. So this is the startup cost. This is the startup cost. So what we are doing is startup cost. Okay, so while increasing the startup cost, while increasing in the startup cost, it depends on the time. So after time, sometimes what we are doing is we are just turning off. We are just turning off the startup cost slowly. So this comes to cooling. So this slowly depend on the hours. So this comes to cooling. But even though some amount of temperature remains, so that that cooling, that heater can be used for banking, that is banking, so that it may be utilized for operation of next hours. So after few hours, slowly the temperature will remains, and also startup cost also might be there. Why? Because we have spent some amount for generating the power, no? So that startup cost also not going down. So it is remains for sometimes. It remains constant for sometimes, so that we might be utilizing the same heat for running the plant. Yeah. So next constraint is hydro constraints. So we can't tell only the thermal generating units. That may be of hydrothermal. Hydrothermal constraints also comes into the account. So in that, if you take like there are some must run generating units. Some units are given as must run status during certain times of a year for a reason for voltage support on the transmission network for such purpose as a supply of steam for use outside the steam power plant itself. So some units are given as given a must run status, must run status. So some generating units, if you take like in 365 days, that plant will work almost for 300 days or 320 days like that. Why? Because there are some units. It has to be. It is called must run generating unit. So until otherwise some maintenance is there, then they can off that generating unit, or otherwise it will run almost for an year, 365 days. In the 365 days minimum, it will run for 350 days like that. So these are called some must run generating units. Must run generating units in the sense, so that generating unit will run for some years of time, sometimes, so that like voltage support on the transmission lines also will be always gradual, so constant for some other purpose. Sometimes for reactive power generation also, there are some must run generating units. They will run that reactive power generators even 100 megawatt or 200 megawatt for almost 365 days. There will be some units of generators. So if they on first generating unit today, they will on second generator, they will on third generator, like that they will be on. But always that plant will be in operation. Why? Because to supply the reactive power, that generating unit has to be run, so that you will get maximum power. So next thing is that fuel constraints. So fuel constraints, a system in which some units have limited fuel, or else have constraints that require them to burn a specific amount of fuel in a given period, presents a most challenging unit commitment problem. So some units have limited fuel. Okay, so some units have limited fuel, only this amount, this tons of coal only available. So with this, we can generate 500 megawatt only. But with respect to constraints, so what we have to do is we have to burn optimally. Optimally, we have to burn. So 500 megawatt generation is there, but only the demand is around 200 megawatt only. So in that scenario, we can go for operation of like a very small generating unit. Instead of turning on thermal generating units, we can go for generating the units from hydro units. Why? Because thermal generators minimum, it started from 500 megawatt, 1000 megawatt, 1500, 2000 like that. So there will be not like 100 megawatt like that. Maybe there, but only for reserve purpose. They are it is having, not in the normal operation. They will not go for this minimum generators, that is minimum rated generators, because we are spending more amount of money for generating the power, and also boiler once it heated up, so that much pressure and that much steam pressure is being generated. So that much that might be maximum utilized. So they will go for minimum 500 megawatt to maximum 1,500, like that. They will not go for only they will not go for okay beyond this 500, like minimum of 500 megawatt. They'll not go for 100 or 200, like that. In hydro, it is possible. Hydro, it is possible. Why? Because the penstock, the penstock, there will be of there will be of series of parallel penstock will be there. So from that penstock, so one penstock will be connected to certain generators, runners. So that with like 10 penstocks will be there, 10 generators will be there. One is of 100, one is of 200, one is of 500, like that. It depends on the penstock size and the dam location and the amount of water present in the particular dam, high head dam or low head dam. Like low head means a minimum 90 feet, 90 feet, up to 90 feet. A higher it means greater than 120 to 150 feet. Like that, it depends on the amount of water, and as well as so that they may go for easily. They can turn on and turn off. Like only it will take 5 minutes or 10 minutes. So simply like that in valve, in valve plant, some valve unit will be there. In that valve plant, simply they will off and on the water to the pinstop. They will off and on, so that whichever which like 1 2 3 they will number. So which penstock if you want to on, they will tell like the third penstock you have to on, so that you can generate 200 megawatt, 500 megawatt, like that they may go for. So and also hydro, only 100 200 500, like that only there. 1,000 sometimes, like if the dam is like penstock size is very very heavy, and sometimes it might be located in very steep places where the dam is located like 5 kilometers or 10 kilometers apart from the dam. Then they will go for like 500 or 1,000, like that. But only few majority of the generators are rated from 100 200 500, like that. Only few generators might be of higher rating you, because that much pressure we have to get for turning that turbo runner of 1,000 megawatt, like that. Next is yeah, so the fuels also very very playing a very very important role in hydrothermal, scheduling thermal generating units. So next constraints comes to spinning reserve. Spinning reserve is defined as total amount of generators available for all units synchronized, that is spinning on the system, minus the present load and the losses being supplied. So what is meant by spinning reserve is nothing but, so total amount of generators available from all the generating units synchronized, minus on the system, minus the present load. So generation minus the present load. So if the demand is very very high, so demand is very high than the generation. Say 500 megawatt is generation, and the demand is 550 megawatt, okay, or 510 megawatt. 510 megawatt is the demand, but generation is only 500 megawatt. So 10 megawatt is the deficit. Okay, 10 megawatt is the deficit, and also whatever the generation, there is some losses also. So 500 megawatt will not reach at the load also. So some 20 megawatt or 30 megawatt, so 470 megawatt, and the demand is some 500 megawatt. So 30 megawatt is the deficit. So that 30 megawatt, what they will do is they will go for spinning, generating the power by spinning reserve unit, spinning reserve generating unit. There will be some spinning reserve generators in substation, and as well as in generating units also sometimes spinning reserve they might be going for, but majority of the time in substation only they may go for this spinning reserve. So there will be some generator of some 1 megawatt or some 2 megawatt like that. The generator will be there in this substation itself. What they will do is they will just on for if there is a power deficit for, or some voltage will be going down, or frequency will be going down for sometimes, like 5 to 10 minutes, they will on this spinning reserve for only, because for generating 1 megawatt or 500 kilowatt, it will take a more amount of diesel is required to generate 1 megawatt itself, even though we are generating for only 10 minutes or 15 minutes up to half an hour. So it will take more amount, like diesel cost is very high today, like 90 rupees per liter. So in that scenario they will go for only um, they will go for only on this particular generator for only few hours, only few minutes, maybe not hours, maybe minutes, some 10 minutes to 15 minutes, up to maximum half an hour they may run. So for maintaining the frequency constant, or for maintaining the voltage under some particular time, they may go for this spinning reserve for sometimes only. So for they have to give the reliable supply, no, so in that scenario only they may be going for this kind of spinning reserve. So spinning reserve must be carried so that the loss of one or more generating unit does not cause too far a drop in the system frequency. Okay, so again I repeat, the spinning reserve must be okay carried so that the loss of one or more unit does not cause too far a drop in the system frequency. So if there is a drop in the system frequency, only they may on the spinning reserve for only certain time, only few minutes of time. If one unit is lost, the other must have ample reserve on other units to make up for loss in a specified time period. Only for very small amount of time period only. For specified time period only. Why? Because we are running the spinning reserve generating unit only in the like substation only, and also sometimes in the generating units we can go for a spinning reserve, like a reserve generating units is there. So like once the this unit is ready, some fault might be happened in this particular generating units. So what we'll do is some reserve generator will be always there, so that will be maintained always. So maintenance and operation always that will be. So sometimes they will go for that spinning reserve generating unit also in the generating units, or in substation only. This will be run for specific period of time.